Hello students and welcome again to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about radioactive half-lives. And I'd like you to write down this definition for half-life. And it says, um, what is the amount? It is the amount of time it takes for half of a radioactive isotope to likely to decay. So in nature, we have these isotopes, a variety of different atoms that are going to decay and turn into something else. Okay, they're going to be either giving off an alpha particle or a beta emission. So what we do is we record how we measure that is through a term called half-life. And now if we come down here, there's a graph that kind of represents this concept, okay? And this green line represents what we call the parent isotope. And this pink line represents the daughter isotope. Now, the difference between a parent and a daughter is the parent obviously comes first. The parent isotope is the one that we are measuring against. It's the one that we are trying to observe, right? One of our common isotopes that we measure for radioactive half-lives is carbon 14. Okay, so carbon 14, okay, is a radioactive isotope of carbon. You've ever heard of carbon dating? That's the isotope of carbon we're using. And carbon 14 is going to decay over time, and it's going to turn into nitrogen 14. Okay, it's going to have a beta emission where a neutron turns into a proton and it releases a beta, an electron, a beta minus decay. Okay, now this green line would represent the carbon. Over time, that carbon is going to decay, and it's going to decay again and decay again. And it's half-life. It's the amount of material, half of the material that is decayed is what we're measuring. So if we started out with, to say, 100 grams, okay, and a specific time of half-life, we're only going to have 50 grams left over because it's going to start decaying. So how long does it take for that to occur, right? In this example, it takes about 5,700 years. In about 5,700 years, our carbon 14 is going to turn into nitrogen 14. And this pink line represents the daughter isotope, which is what that carbon's turning into. And our nitrogen is going to meet at this point right here, okay? So we're now going to have zero nitrogen in the beginning, but after 5,000 years, its half-life, now half of our carbon is now turned into nitrogen, okay? And if we do another half-life, we do another 5,700 years, okay? We now have less carbon, and now we have more nitrogen. And this trend increases. It goes a half to a half to a half to a half, right? So if we look here, we have 100. Half of that is 50. Half of that is 25, half of that is 12.5, and you can work your way all the way down into this exponential form here. And this will actually never really reach zero, but you'll likely have less and less over time. At a certain point, it's a pretty small amount. While on the flip side, our amount of nitrogen that's forming it's growing inversely of that. So as our carbon goes down, our nitrogen increases. So it's recognizing this trend where as our carbon 14 is decaying, our nitrogen is increasing because that's what it's turning into. Okay, and we're using this in terms of half-life. How much time does it take for half of that carbon 14 material to turn into nitrogen? Okay, and in the case for carbon, it's 5,700 years. For other materials, it's seconds. It could be hours. Okay, let's flip the page here. I want to show you a graph here. Okay, and this graph just shows you the duration of times for something to decay. If it's in this outer area of this band of stability, it's going to decay in less than a second. While if you look at this black line, that's where stability is. The odds of them decay. The odds of those atoms decaying are pretty low. While if you look at this orange, it's seconds to years. While some of these yellow ones take years up to thousands and billions of years in the future to decay. Okay. Now, you don't have to memorize this. We're just appreciating it. That's based on certain isotopes, they will decay at different times and different rates. Okay. So keep in mind, you don't need to memorize this, but you do need to understand the term of half-life, and understanding the concept of this graph will help you understand the relative amounts of parent to daughter isotopes. Okay. Thanks for watching.